Knock, knock, knocking on heaven's door. Wow, 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 wow. Okay, so today we're going to talk about inductance. And to talk about inductance, we need to talk about inductors. And before we get into our talk about inductors, we need to talk about flux. F-L-U-X, that spells flux. We need to talk about it and what's going on here. Okay? Now, normally when we talk about flux, we can think of flux as an amount of stuff or amount of something going in or out of some container or some surface or some volume, okay? And a real easy way to think about flux is, imagine for a second you have a bathtub, okay? In this bathtub, water is, entering into the bathtub at some rate. This will cause the bathtub to fill up. Well, as water is coming in, this would be like a positive flux. You've also got a drain in your bathtub, and the water is going out. So this is some negative flux. So this is like the influx or the outflux of water. But you could also have flux of like a classroom. Students walk into the room. Students walk out of the room. People are going in, positive, going out, negative. You could have a flux of pretty much anything. Now, within the world of physics, we like to talk about flux in terms of two things. One's an electric field, which we're going to get back to that later. But it's helpful to talk about the flux of a magnetic field, a B field, for what we're going to be doing with inductance. Now, in the bathtub, it kind of makes sense that you're filling this up with water and like the water is contained here and then the water goes away. But we're going to think about flux not as like filling a surface or filling a vessel, but we're going to think about flux as some amount of this B field, that's our something, passing through a surface. Okay, so imagine for a second that we had some shape. So here's like a circle, right? Well, that's a terrible looking circle. Here's a circle. And we could imagine that the B field could come like through the circle, right? Like if there was a, sheet right here, that B field could go through the circle and come out the front, just like this. That is the flux we're talking about in this scenario. The B field is an amount of flux going into or out of a surface area in this case. And we're going to talk about the flux entering into a surface. That's what we care about when we're talking about a magnetic flux. Now, this will make more sense as we continue to talk about it. But in general, we are going to use the symbol capital Phi for flux, and we're going to subscript it with a B field. So we know this is a magnetic flux, okay, different from an electric flux. And like I said, it's really, if we take a look at some area here, in this case an area of a circle, how much of this B field is going through that circle. Now, if we think about it as, we have a circle here, and a B field's going through this circle that exists as we have drawn. How could we generate more flux? How could we generate less flux? And there's a variety of ways we could do this. Well, we could generate more flux by providing more B field. We have a larger B field, and as a result, more flux. That makes sense. That's an easy one. So if your B field goes up, your amount of flux can go up. Subsequently, right now, our circle's only this big. What if I drew a larger circle? Well, if I had a larger circle, I could get more B field through it because I've just got more of a cross-sectional area to play with here. Okay? So if the cross-sectional area increases, the amount of flux can increase as well. Assuming, and this is assuming, that that area that you've increased to is still within the B field. If you've increased the area, but you haven't actually gathered any more B field, then that doesn't really help you, right? So the area increasing will increase the flux, but only if you're grabbing more of this B field. And then there's something else going on here with flux. And this is a little weird. So this is our circle we had before, kind of drawn like at an angle so we can kind of see what's going on. This is the circle drawn from the front, and this is a circle drawn from the side. So you can't really see the entirety of the circle, you just see like an edge of it, like if you were on flat. Now, the way we take the direction of a surface in mathematics is we look at the surface normal, Okay, what is the normal vector here? And if I take a look at my circle, my normal vector is actually pointing out of it. This is the direction normal. It is the direction 90 degrees. Here it would be like pointing out at the board at you. That's our bell. Do you know what time it is? So we take a look at our orientation of our circle here is given by some normal vector, okay? And the orientation of any surface or plane is given by the normal vector, which is perpendicular to that surface or plane. Now, our B field is also going through this circle, or this area that we've kind of cut out, okay? It's going through this loop. These are in the same direction, and because of that, we have a flux. We have a circle here, and the B field can go through the circle. But what if your circle was set up differently? What if your circle was set up such that it was resting like this, and its normal vector was up? Well, now if our B field is still going to the right, we're not getting any of the B field to go through that circle anymore. Like, that's like our circle's flat and our B field is just going zero right over the top. So here, when our normal is parallel to the B field, we have a large amount of flux. But when our normal is perpendicular to the B field, and that designates the direction of the circle, then we don't get any flux. So it turns out that this flux here, a magnetic flux, can be given by the magnetic field vector dotted with the cross-sectional area, because that area vector is dependent on the normal. You normally don't think about areas as being a vector, but the orientation does matter here. You know, and if we think about it like this, if we had our hoop slightly tilted so that our normal was pointing up like this, well, we would catch some of that B field. Okay? So the dot product here does indeed matter. We do need to look at what is the angle between these normal vectors and the B field. What is the angle that our hoop or whatever, you know, shape or surface area that we're going through, how much has that been tilted? Okay? So kind of a neat thing there. The other thing that matters is there's nothing stopping us from just having one hoop. We could have 2 hoops, or 3 hoops, or 4 hoops, or 5 hoops. We could have n number of hoops here. Okay? So NBA is some magnetic flux that we can have here. And another way we could write this is we could just write this as NBA, and that dot product we have here represents the cosine of theta. And that will give us some amount of magnetic flux. Thanks, Bell. Okay, so that is just the idea of a magnetic flux. Now, the reason why we need this magnetic flux here is that we are going to find that if we have a changing magnetic flux, so if we have a either changing amount of B field or a changing amount of cross-sectional area or a changing angle or all of those, if we change the amount of flux that we have in some amount of time, because, you know, time has to keep propagating forward, that will actually induce for us an EMF. But it's going to happen in kind of a weird way. The EMF we're actually going to generate, or the voltage we're going to generate, is going to be given by the negative change in flux, magnetic flux, in some amount of time. And if you wanted to, there is an N term that pops up here, so bloop, there's an N. And if you wanted to write this in fancy schmancy calculus, it'd be negative, and then it'd be like an N if you wanted it, but we could really just think of it as d flux by dt, okay? Some people also don't put the N here. Some people just think, hey, look, the flux was a part of N to begin with, because it was up here, so like I'm double counting it. It really depends on how you want to think about it. Some people like just running it without the N and then saying afterwards we'll multiply it by however many loops. Some people like to include the loops and then just shove it into there. It really depends, you know, potato, potato, where do you want to put that? It's just some scaling factor you have. It doesn't really matter. But this is what we're going to be talking about here. We're going to be talking about this idea of a magnetic flux, which we have, and then how that flux will induce some EMF, okay? And this negative sign is kind of interesting. We'll talk about that in the next video when we get into another right-hand rule. But until then, adios. We are finished here. You take it easy.